Hello, hello. So we're gonna start the lecture on time today because we have still a lot to finish by the end of the semester, and we did lose one lecture um, when they announced that all courses are going on Zoom now. So we're gonna try to shed off some material and then just to be able to cover what I would like to cover. I sent out a survey today asking you about muddy and clear points regarding the ODE lecture so far. So you can wait after today's lecture and fill that out, because today we'll finish the initial value lectures on initial value problems. I'm sorry I didn't do more of those. We did them once, if you remember, but then, you know, this whole mess kind of started. We couldn't do more of those, and the goal is to address your concerns, your questions. And the survey is anonymous, but if you insist on having a question answered, put your name at the end of your answer, and I'll make sure to address that in a document and then put it on Canvas. Okay. I hope you're all doing well. We're almost done with the semester. I released a homework assignment today, which is going to be due next Thursday. But then the week after, we're going to have the final exam, but I still need to pass one more homework by you. And I'm going to have to release it sometime next week. It's going to be on boundary value problems. So we'll see, maybe I'll shrink it a little bit so that you have enough time to at least cover it, because I'd like to have a boundary value problem on the final. So I hope you will be understanding in that regard. Again, I'm not trying to, we're all under pressure, okay? All of us, trust me, you know, myself included, having to turn everything kind of online and redo all my exams on Canvas. Everything just takes a lot of time. And I know on your end, you're just kind of juggling and struggling things, new policies with the syllabus. So we're kind of all in this together. So let's just bear through and be done with the semester. It's one heck of an experience for sure. Okay, last time, first let me ask you, do you have any questions, concerns, comments about things from last lecture? Okay, great. So today, yes.
I was just wondering, are the exams done now? I guess I was just wondering in general.
Pardon me?
The exam 2 regrades?
No, I haven't.
Okay.
I still have about 15.
Okay.
Yeah, I think I haven't gotten to your
Okay.
request, but you will hear from me in an email saying done. Go check your comments. So whether you get partial credit or not. Okay. So if you haven't heard from me, it means I'm still working on it. Okay.
Sounds good. Thank you so much.
Okay, thank you. Okay, so last time we finished off with the forward Euler method. We had discussed a form that I'm showing here, saying that the value of the quantity phi in the future at n+1, at time level n+1, is equal to things from the past at level n, things that we know. So phi n plus delta t, that's the time step size, that's the interval size, the distance between any two time points, times the right-hand side of the ODE evaluated at n. So everything on the right-hand side in this equation, can you see my cursor on the screen? Yeah, so everything on the right-hand side over here is known, okay? You should agree with that. Well, you can disagree if you want, but I hope you agree with that. Everything on the right-hand side is a known quantity. On the left-hand side is unknown. So this is technically just an algebraic equation. We can just solve it at every point. That's why this method is so great and so useful. I'm going to skip through the video. So when I posted the lecture on YouTube, I got a copyright warning that this was taken from Hidden Figures. And I was like, hey, I'm actually advertising this movie for you. So anyway, but no issues there, because this is all fair use for educational purposes. Anyway, so we went through and did this exercise in class. You all got the right answers, etc. I'm just going to kind of go through it very quickly, and let me just skip to the end. I just wanted to remind you of the forward Euler method. Okay, actually I could have started over here. So this is the forward Euler method. Now we're going to hit our first activity, And taking this forward Euler method, phi n plus 1 is phi n plus delta t, or h, right-hand side, t n phi n. Again, r could be anything. It's just the right-hand side for a differential, for an ordinary differential equation. Your first programming activity, you got 2 minutes. I want you to think about writing an algorithm, a pseudocode for doing this forward Euler. So ask yourself the following questions. What does my routine, which we're going to call forward underscore Euler, what would you like it to require? What are the least quantities that this routine requires? What other optional quantities you'd like to add to it? And what should the routine return? Just like with everything in programming, right? So there's usually like a minimal set of inputs you need for a routine and at least one output. So I'll give you a couple of minutes to think about this, and then we'll implement it together, okay? Actually, I'll give you 1 minute. Everything is on sale now, so I'll give you 1 minute rather than 2 minutes. I'll discount the minutes for you. Just a pseudocode. Say, you know, first step, define forward Euler. This is what I need. Do I need time step size? Do I need time? Do I need old phi, new phi, whatever? Okay. Now you can be inspired by ODE int, what that requires, okay? Okay, time. All right, let's see. Hyung-Shu, do you have any answer for us? Hyung-Shu, are you with us? Apparently not. Let's see. Am I gonna pick? There's always a set of people that I always end up picking. Let's see, David W. When? Yeah.
I am here, but I don't have an answer on this one.
Okay. Let's see. Rachel.
Hi.
Hello.
I think we're supposed to return the phi n plus 1.
Okay, that's correct. Absolutely. What would you think the routine requires?
Not sure. Like defining or?
Yeah. So define forward Euler. What do we need to pass to this forward Euler routine?
The right-hand side?
Okay, yes. You are correct. Don't be embarrassed. Yeah, absolutely. Let's see. Do I have any takers right now? Volunteers? Anyone who could give me a pseudocode for writing a code for forward Euler method? So we have a partial answer. We need at least the right-hand side, of course, right? And it's gonna return phi n plus 1. What else do we need? Don't we need delta t? Yes.
You need to make sure that you have all the constant values defined. So your step size, your function r, and then I know we use an array of t values that we can test it at.
Okay, so you're right. So we need the delta t value, and we need the initial condition, like you said, and Paul is saying on chat. Okay, so let me give you, obviously there are multiple answers to this, but at the least, if you want your forward Euler, I want my forward Euler method. I don't want to keep calling it every time I want to get phi n plus 1. You know, I don't want to keep calling it to get phi 1 and then get phi 2. I want to call the routine, give it the ODE, and I want it to give me the full integrated function, just like ODE int, right? So if I give it a set of points and time, or I give it an nth time, I want it to just integrate the entire function, give me and return the entire value. So rather than returning only one value for phi n plus 1. I want it to return a set of values, an array of values. So the way I would do this is, one way I would do this is as follows. So I'm going to mimic what ODE int required in the list. It's going to require a right-hand side function. So again, that's just a name of a routine for the right-hand side, similar to what we did with ODE int. We just define the right-hand side. Think of the right-hand side for the convective heat transfer problem or the radiative heat transfer problem. And again, we're going to assume that the right-hand side is going to depend on T and phi, correct? So I'm calling things F over here. I also need an initial condition. I call it F0. And I need an array of time points. I call that T. Okay, that's one option, right? But in the list, I need right-hand side, I need F0 and a time step size. Now, the array of time T, inside of it, I can extract the right-hand side, the delta T, right? Because, you know, let's focus only on equally spaced points for time. Taking the difference between any two time points gives you the time step size interval, right? So that gives you delta T. So embedded in the array for T is the time step size, okay? Next, programmatically, I want to create an array F for the solution, okay? So inside this routine, I want to create an empty array for the solution. I want to initialize the first point of the array with the initial condition, right? If my F array is the solution, the first point needs to be the initial condition, and then subsequent points are going to be computed using the forward Euler method, which we will do next. We will loop over all time steps, and we can get the size of the number of time steps again from the array T, because once you have an array, you can get its length and the interval size, right? And from that, we just loop over the time steps and simply update, say F at n plus 1. So this would be a loop over n, starting from point 1 to the last point. And we could say F at n plus 1 is F at n, exactly like the formula, plus delta T times the right-hand side. Now remember, we said that the right-hand side needs to be defined to at least accept a function value and a time value. So now going back to when we discussed ODE int, and it was mysterious somehow that we defined the right-hand side to take two variables at least, phi and time, if you remember. This is why we need phi and time, right? Because that right-hand side is R at Tn and phi n. So what we need to pass the right-hand side is the value of phi at n and the value of T at n, okay? And this is how you do it, all right? Now, right-hand side is a routine, Python routine. We defined that last time. We're going to do it again today, okay? And then finally, we just return F, okay? So programmatically in Python, I'm giving you the code here, and then we'll do it together in Python, see how it works. So def forward Euler, it's going to take right-hand side F0 initial condition and a time array T, okay? And here we're implementing Fn plus 1 is Fn plus delta T right-hand side. First, I need the number of time steps, and I can get that from the length of the time array. So n steps equal len of T. So that gives me how many time steps or how many points there are in the solution, okay? Pardon me. And that is controlled by the user, because when the user calls this routine, the user is going to provide T, the length for T, okay? Next, we compute delta T. Here, we're assuming that delta T is constant, so we can just take the difference between any 2 points in the time array. And I'm going to take, you know, the difference between T1 and T0. Okay, that gives me delta T. Then I declare an array of zeros for F, just, you know, an empty array, essentially. And the size of F has to be n steps, agreed? Because those are the time points at which we're getting the solution, all right? Then I initialize the first point, F at 0 equal F0. And here's the loop. For n, in np.a range all the way to n steps minus 1, because we don't hit the last point, because that last point is computed automatically, right, with Fn plus 1. So we need to go from 1 to n, from 0 in the indexing, from 0 to n minus 1, right? And that will fill out F1, F2, etc., all the way to Fn, okay? And then we return F. That's how we do it, okay? Now there's another form also that I'd like to share with you, because in this form over here, we assume that the user is passing the array of time, and that means that the user has to define delta T when they define the array of time. Another option would be to actually, rather than passing an array of time, we pass the end time. So say I want to do this for 10 seconds and pass an interval size. I say, you know, I want to go to 10 seconds and with this delta t, 1 second. And then inside the routine, you build a linear space for the time array, okay? And then you do the same thing as we did before, but then in this case, I would return the time array and the solution as well so that I can plot them, okay? Anyway, let's go ahead and exercise what we learned here now. I want you to download, we're gonna go back to the lobster example, and I want you to re-download it because I added some code to it. Go ahead and download it again from Canvas. You talk about what you define a right-hand side. Yeah, so there's a question here about how we would define the right-hand side in the code. We spent over pretty much the entire lecture last week doing that. So I would recommend you go over that, please, last lecture. We'll cover it very quickly over here today, but please go back over the previous lecture, okay? All right, so go ahead and download the lobster example with gaps, re-download it again because I updated it today. And I'm gonna open it on my end and then we'll go through the exercise together. Okay, let's see. Localhost. Okay, do we all have the notebook in front of us? Yes? Okay, so last time you had filled out these guys over here, right-hand side convection and right-hand side radiation. Let me see, pass parameters to the right-hand side, and then using our own integrator. Okay, so what I will do here, so again, the way we define this right now, we're not passing extra arguments to the right-hand side function, okay? What I'm trying to do here is just illustrate how things work. We can work on adding features to pass arguments to the right-hand side. It works similarly to ODE int, but that's not the point here. The point here is to get you some mileage to see the inner workings of ODE int and why it requires things in a certain way, okay? So what I'm gonna do, what I'd like you to do is just fill out the, so go copy this. For some reason, my editor is not clicking. So copy this RHS conv1 and copy it and put it in RHS conv. We're still missing two things here, which is H, say 500, and Tinf, let's say 375, or yeah, 380. Let's say boiling temperature, boiling temperature of oil, of the oil, okay? Heat transfer coefficient, all right? So again, that we did this last time, and then we found it was annoying to change these values inside the function. So we kind of define them as arguments, but you know, we're not gonna worry about arguments right now. Let's just define the standard right-hand side for the lobster problem. And again, for radiation, go ahead and copy the RHS radiation 1 and paste it over here, okay? And we're missing one thing here, which is T infinity for the oven, and that's 500 oven temperature near broiling condition, okay? Okay. And if you don't remember the equations here, you can go back over the last lecture, but we also covered this. Hold on, is there something missing here? Yeah, so this was the ODE for the convective heat transfer case, and the ODE for the radiative case was this guy over here. So that's the right-hand side. That's how we program it. For those asking how we program the right-hand side, is just simply a routine in Python, but that routine always has to take at least the dependent variable and the independent variable. But those are not arrays. Those are individual specific values at time level n, and now you see why we need that. Okay, it's because of this formula over here, right-hand side at n. Okay, the right-hand side evaluated at n. Okay, so go ahead and start evaluating your cells. Okay, at least these 3 cells should just execute without any issues for you. Are we all on board? Anyone having issues? Okay, no issues. Great. All right, so now we will, again, last time you can execute these cells over here. Oops, main forward Euler is not defined. Okay, don't forget about this cell. Okay. Okay. And last time we used ODE int, and we filled out the gaps over here. But now we are going to go and use our own integrator. Now what I did, I went ahead and already programmed in what I showed on the slide. So I defined the forward Euler method. Again, takes right-hand side, initial condition, etc. And then you can execute this cell and it should execute. Okay, so now it's time to try out our integrator. We're going to start by defining the linear space for time, because we defined our forward Euler method to take a linear space for time, just like ODE int, okay? And the way I like to do this is actually define my desired time step and say I want a time step of about, in this case, 10 seconds, okay? And the t end was defined to go up to 20 minutes. So, but because all time is in seconds, so we multiply this 20 minutes by 60 seconds to give us things in seconds. And then I define a number of steps, a number of points on the time interval, okay? And that should be an integer. So we simply take t end and divide by the time step size, okay? So that gives us a number of steps, okay, to go through, all right? Number of time steps. And then we create a linear space for time simply by saying np.lin space. We're going from 0 to t end with these n steps. Okay, so if you're not comfortable that this works, you're not convinced that this works, just simply print it. Okay, print time. Okay. Alternatively, if you don't want to define your delta t, just define your n steps. Say I want 100 points on the interval, and then it will create the 100 points for you, okay? Either way, and then you can print out your delta t. You can say print my delta t is equal to time 1 minus time 0, or time 2 minus time 1, any difference between any 2 points, okay? So this is giving you a delta t of 12 seconds, okay? Either one works, all right? And then our initial condition we said was 311. And then simply we call the forward Euler twice here. The first one for the convective case, and we give it Paul, download the most recent, please download the most recent. It's already defined for you. Download the most recent lobster example with gaps. It should be on Canvas. Okay, you guys all have that? Yeah? Hello, anyone having issues with the, okay, you all have the forward Euler. Okay, great. So for those of you who are not listening, please download the most recent lobster example with gaps. Okay, it has all of these functions defined in it. Okay. Okay, so now we are ready to call to the forward Euler, and the forward Euler needs a right-hand side, an initial condition, and a time array. That's what we're gonna give it. We're gonna give it the first time we're gonna call it, we're gonna give it the right-hand side for the convective case. And again, you just give it the name of the function, okay? Because internally, we're gonna call, internally when you pass RHS conv to forward Euler, it's gonna take it as RHS, and then it's gonna call it inside here, okay? And then we give it the initial condition T0 and the time array. And we're gonna call this twice, okay? Once for T convection and once for T convection and once for T radiation, okay? And forward Euler is gonna return those solutions, all right? So let's see, let's run it. It should run. Okay, great, go ahead and run it. Okay, No issues there, I assume. Did anyone have issues running this? Nope. Okay, great. Now we are ready to plot. So what are we going to plot? We're going to plot the temperature versus time. Okay. Abigail, you having issues? You having issues?
We're still trying to figure it out. Because we were using the stuff from last time.
We downloaded the new one.
We downloaded the new one, but we were still using some of the code from the last time, and they have H and T in, so we've got to go in line.
Yeah. So I went through that. I just went through that. So okay. All right. So let me repeat some. Okay, I may have gone through this faster than you guys were able to follow. Like I said, last time, remember we had to define another set of functions to pass parameters to the right-hand side. And what you could do is just copy the RHS conv1 and put them in RHS conv, which doesn't have the parameters in it, and just simply define the parameters in there.
Oh, okay.
Okay.
Yeah.
So same thing, Paul, we're not using RHS conv1 with our routine because our routine doesn't allow us to pass arguments. Okay. Who else is having issues with this? So again, we had two right-hand side routines. The first one in this, at least in this new lobster example with gaps. I know last time we modified everything. That's why I put in a new lobster example with gaps. But what I want you to do is focus on the right-hand sides that do not have arguments in them and just fill them in by copying from the ones that have arguments and then define the arguments inside the functions. I know it's kind of few mouthfuls, but just copy from RHS conv1 and RHS rad1, put them in RHS conv, RHS rad, okay, and then redefine whatever is missing in there. For conv, we had to redefine H and T infinity, and for radiation, we had to define T infinity. Are we on board?
What are the values there for H and T infinity on both of those?
I put in 500 and 380 and 500 for T infinity for the radiation. So they should be highlighted on the screen right there. Okay. Anyone still having issues with the right-hand sides?
I'm just wondering for later. So just move the define forward Euler above, right? Just because like I know that like we kind of applied the forward Euler in the notebook earlier than we define it.
Yeah, so that's why I
Okay.
had to delete those cells. That was a mistake. Those cells shouldn't have existed there.
Okay.
I forgot to delete them before uploading the notebook. Okay.
Okay.
I
Sorry.
apologize for that. So just delete those. Follow the chronologically what we did last time. We first used ODE int, right? And then we passed parameters, right? And then used ODE int again. Now we're going to use our time integrator, and this is where you define the forward Euler. Okay. Okay. So now we are on board. We execute this, gives us temperature with convection, temperature with radiation. Now we can go and plot. What are we plotting? Temperature versus time, right? And I like to plot things versus minutes. So I'm going to take the time array and divide it by 60 to give me minutes. Okay, you can plot with respect to seconds. Doesn't matter. It just changes the value of the number. And then if we run it, it gives us exactly what we expected to see last time. Okay.
So your axis is in minutes, correct?
Yes. Actually, I have a typo here. So time in minutes. Thanks, Dylan. Okay. Right, because I divide by 60. If you don't divide by 60, you have to call it seconds. But then, 600 seconds, 675 seconds. I like minutes better in this case. It has to do with time scales, right? So these things are going to take minutes to cook. So let's just report time in minutes. Okay. Okay, anyone having issues? So, you know, the point here is you don't expect to kind of, for this to just kind of sit in your mind immediately. You have to spend time on reviewing this code, okay? So go take this and then spend time, try to understand how it worked, change some numbers to make sure it works for you, okay? Any questions on anyone still having issues with this? Okay, so Paul is good, that's great.
I guess my question is, why is it that we're not using the, are we using the args argument still with the forward Euler this time?
No, Katrina, so what I said is, right now, for the time being, we're gonna define forward Euler on our integrators that we're defining in class. We're not passing extra arguments. To pass extra arguments, we're gonna have to get into pointers, and I don't wanna get into pointers, okay?
Oh, okay, so you have to delete them from the original RHS
Yes,
column.
that,
Okay.
or define new RHS. That's why I call one of them, I put _1 and the other one without one. To pass extra arguments, you have to put star args over here, argv, and then you have to loop over the arguments. It just opens up a different kind of worms that, you know, I'm not saying you guys are not ready for it, but that's something you can pursue on your own. We're going to be using ODE int for the rest of the semester, so not to worry about this. Okay, so what I have here at the bottom is something extra for those who want to dig deeper. So if you execute the cells, okay, I have an error over here. tconf 1. Okay, let's see, conf 1 lab. Okay, ODE does not define. Never mind. 1 second. Okay. From scipy.integrate import. You're not responsible for this, but it's something extra that I thought some of you may be interested in seeing how powerful Python can be. Okay, so remember last time we were like changing values every time we'd go type in a value and go and see what happens. Look at how cool this is. So here I'm changing h and it's automatically updating. I'm changing t infinity for the fluid, you know, so I can maybe go to 100 over here, and we can change the baking temperature over here, and it will automatically do the integration for you and show the plot. So this gives you a better idea, a faster way of kind of analyzing your system. All right, feel free to dig into these widgets. It's really cool and easy to do. If you want to play around with that, that's for you to do. Okay. All right, are we all good so far? Okay, great. Now we are gonna jump into the next step, the next part of initial value problems. And so far we covered explicit time integration, right? The other extreme is implicit time integration. And we're gonna discuss first a motivation for doing implicit time integration. So the reason we called explicit time integration explicit, not because it was explicit, you know, it was because we could just immediately solve for the value of the future, value on the future. There was nothing, it was just obvious, right? It was just right there, phi n plus 1 equal things from the past, okay? So that's why we called it explicit time integration. Now we're gonna look at the other extreme, but I first want you to download the following notebook called Motivation for Implicit Methods with Gaps, okay? So go ahead and download that, Motivation for Implicit Methods with Gaps. Actually, let me see what I put on that one. Motivation for Implicit Methods with Gaps. Okay, okay, great. So it really doesn't have any gaps. It's just to allow you to follow through with me, okay? So what we are gonna do, did you download that? Motivation for Implicit Methods with Gaps. Okay, all right. I'm gonna assume you have it downloaded. Anyone doesn't have it downloaded? Okay, perfect. All right, so in this next step now, we want to use the forward Euler method to solve the following ordinary differential equation. d phi by dt equal minus 1000 phi. Okay, so we expect that starting with an initial condition that's 0, we expect the solution to just, starting with an initial condition of 1, we expect this to just decay, okay, to just go down, all right, keep decreasing and decreasing and decreasing, okay? Now, we think that the forward Euler method should be able to solve this, this particular problem. That's what we're going to test now. Now, what is characteristic of this ODE is something that you will see as a chemical engineer, and specifically it happens with chemistry and chemical kinetics. Sometimes when two reactants meet each other, the reaction rate is so fast that you see a change in concentration, a very sharp change in concentration before things settle down. We call this a sharp transient, okay? And if you look at the solution over here, for the most part, there is a lot of change happening in this one region, and then for the rest of the time, nothing much is happening, right? This is a mathematical property called stiffness, okay, that we're going to talk about, and that's the need that requires us to use implicit methods. But first, we're going to try to solve this particular ODE, which is benign. It's d phi by dt equal minus 1000 phi, right? So it's pretty benign. So what we're first going to attempt to do is use the forward Euler code that we just developed together. So you open the notebook, and I want you to try to solve this ODE on the interval 0 to 0.1. We're starting with a time step size of 0.003 seconds, okay? So go ahead and open up your notebook. I'm going to open it up with you. So we execute first cell, etc. Over here, in this first cell, I'm defining the right-hand side of this sharp transient, okay? And that's equal minus 1000 times phi, okay? So again, we define the sharp transient of the right-hand side in terms of the dependent variable and the independent variable, okay? So that's what we define for the right-hand side, okay? And now the exact solution for this function is y naught e to the minus at, and a is 1000 over here, so this is what you get for this solution. Again, not to worry about this. What you have to worry is that this function looks like that, okay? So the exact solution for this ODE is obviously something you've learned you're taking ODEs now as a core requisite. So, you know, with an initial condition of 1, the exact solution is e to the minus 1000 t. So that's why you get this kind of sharp thing. All right. So next we're going to use the forward Euler method. Now over here, I'm defining the forward Euler using my other approach, where you pass the value of delta t explicitly to the routine, okay? Because I want to test different values of delta t without having to worry about creating new Lin spaces, etc. So let the forward Euler method automatically define the Lin space for time internally. So all you have to do is, again, execute this one. Now over here, we define initial condition phi 0 equal 1. So there's a typo on the slides. The initial condition should be equal to 1. And t end is 0.1. So that defines the interval from 0 to 0.1, like I'm asking you over here. The next thing I want you to do is start by solving the system for different values of delta t. So essentially just put delta t and execute, and let me know what you get. So keep playing around with delta t. Larger, should you go larger? Should you go smaller? But what I'm looking for is an explanation of what's going on. Can you find a delta t? Can you find a delta t that gives us an accurate solution? Okay, once someone gets to a delta t that gives you something that looks like the exact solution, just speak up.
I tried delta t is equal to 1 to the power of -5.
Okay.
And that was pretty accurate.
Okay, good. Okay. All right. So, okay, Paul says same thing. Yep. So that was pretty accurate. Okay, so dt is, and it's still solving it because that's a lot of points, but that's kind of inefficient, right? So you're using a lot of points to capture that initial transient, right? But then for the rest of the domain, you don't need that many points, right? But again, that gives you an accurate answer. So here's what we're going to do. We're going to start with 0.003, and you run that, and that obviously gives you something weird, right? I was like, I have no idea what this solution looks like, why this solution is. And then we go to 0.002, and then you get something like this, right? Which is crazy, just oscillatory, has nothing to do with the solution. You go to 10 to the minus 3, and then we're starting to get something. So if you notice here, you get this initial bam drop, and then it goes to 0 automatically, right? And then you start shrinking your delta t, 0.005, for example, and then you start getting answers over here, okay? So obviously what this tells us is that you cannot just choose an arbitrary time step size to solve arbitrary problems. When we did the lobster, we were kind of lucky because the problem was set up in a way that doesn't have these crazy sharp transients, okay? And we were lucky to get by using a 1 second for a time step size. But over here, in this case, there's big change happening in a very small interval of time. And an arbitrary delta t could either produce an accurate solution or a completely garbage, right? Those oscillatory solutions were just garbage, right? Okay, so let's go back to the slides and try to understand what the heck is going on. All right, so if you try delta t, like, 0.003, you get this, and then 0.002, you get that. 0.001, we start getting to a reasonable answer, and then 0.005, it looks like we're capturing what the solution is supposed to look like, okay? All right, so let's look. I'm gonna try to give you a basic explanation. There's a whole theory about what's going on over here, but I'll try to give you the simplest explanation of why this is happening, and that has to do with something called stability, okay? So what we're gonna do is take this standard ODE that looks like the one we solved, d phi by dt. We solved d phi by dt equal minus 1,000 phi. We're gonna replace 1,000 by a, okay, as a parameter. So we're gonna solve d phi by dt equal minus a phi. A is positive, so this ODE is strictly decaying, okay? It's strictly decaying in time, and with an initial condition of phi 0. Okay, next we're gonna try to apply the forward Euler method. And that forward Euler method with this right-hand side tells us phi n plus 1 is phi n minus delta t a phi n. Agreed? Right? And then we rearrange things. We get phi n plus 1 equal 1 minus delta t a times phi n. Just basic algebra. Okay. Now for this particular ODE, we know that phi n plus 1 must be smaller than phi n, because we know that that ODE is strictly decaying. Agreed? It must be at least less than or equal to phi n. So we call that condition stability. Let's just call it stability, okay? So that condition tells us that the magnitude of phi n plus 1, okay, must be less than phi n, less than or equal to the magnitude of phi n. Now, what does that imply in terms of the ODE we looked at just before? It implies that 1 minus delta TA or 1 minus HA must be less than 1. For phi n plus 1 to be less than phi n must be multiplied by a factor that's less than 1, correct? Otherwise, so if phi n plus 1 equal to phi n, it means phi n plus 1 is greater than phi n. But if phi n plus 1 is 0.1 phi n, then that tells us that phi n plus 1, this condition is satisfied. So this implies a condition on h, on the time step size. And that condition can be deduced from 1 minus delta TA less than 1. And that gives us a condition that as long as delta t or h is less than 2 over a, okay, in this case, then we are stable. Then we can satisfy phi n plus 1 less than phi n, okay? And otherwise, what we're gonna get is phi n plus 1 is gonna be greater than phi n, and that's why you see these crazy oscillations, okay? This problem happens when you have competing time scales in a system. And what do we mean by time? What's a time scale? A time scale is a scale of time or length of time at which a phenomenon takes place, okay? In the problem we just solved, we had a very fast time scale. So we had a drop in a very short period of time. And then for the rest of the function, it was constant, correct? For the entire time. So those are two distinct time scales that are orders of magnitude separated from each other, okay? So if all the time scales in a problem are similar, then you don't have this issue. But when you have two competing time scales, one of them that's really fast and one of them that's really slow, then you have issues like this. So fluid dynamics phenomena, for example, are an example of this. So you have things happening at the scale of the entire atmosphere, you know, clouds moving at, you know, kilometers per hour, okay? And then you have local disturbances that are moving at kilometers per second, okay? And meters per second. So those are two distinct scales, and that's why fluid flows are difficult to solve, because we call that property stiffness. Anyway, you're not responsible for all of this, but that basic understanding of stiffness and that you should understand for why a method could go unstable, could give you garbage results. It's because you have a limitation on the time step size. And explicit methods, such as the forward Euler method, is a classic example, or explicit methods suffer from this problem, okay? That's why we need to develop new methods that do not suffer from this problem. Now, the question is, are there methods that can allow us to choose an arbitrary delta t and give us an answer? Turns out, yes. And those are called implicit methods, and that's why we study them. So implicit methods circumvent the stability problem by using information from the future. It's like they can travel in time, bring information from the future, and incorporate that into the solution. Let's see how this is possible. So again, we're going to look at our ODT, d phi by dt equal to the right-hand side. And we're going to assume we know the value of phi and the right-hand side and everything at state n. Okay, so we're trying to predict n plus 1. With explicit methods, what did we do? We evaluated that ODE at time level n. Okay, we took that ODE at time level n. And from that, we used what? A forward difference to approximate the derivative. So we know everything at time level n. We don't know the slope yet, but we can approximate the slope using forward difference to give us phi n plus 1. And that's how we obtained the forward Euler method. It gave us an algebraic explicit relation for phi n plus 1 in terms of everything we know at n. With implicit method, we're going to do something different. We are actually going to go and evaluate the derivative at n plus 1. So we're going to write, although we know nothing at n plus 1, we're going to see what happens if we write the derivative at n plus 1. We're going to say d phi by dt at n plus 1 is equal to the right-hand side at n plus 1. That's a valid statement because the ODE is valid at all of those times, n minus 1, n plus 1, etc. Then we said, okay, we know nothing at phi n plus 1. Okay, we're trying to find phi n plus 1, but I still need to relate this to phi n somehow. So we go and use backward differencing now on d phi by dt. And if you remember your backward difference formula, d phi by dt at n plus 1 is equal to phi n plus 1 minus phi n over delta t. That's the backward difference formula. Okay, so it looks like the forward difference formula for the derivative at n, but this one is evaluated at n plus 1. Now see what happens is that this is an implicit equation because you cannot extract phi n plus 1 directly from this equation, right? And that's why this is called implicit. And this particular formula is called the backward Euler method. Why? Because we used backward differencing. So we evaluated the derivative. We said we're going to evaluate the derivative at n plus 1. That made the right-hand side all at n plus 1. And then the left-hand side, we approximated with a backward difference. We used value at phi n. But that gave us an implicit equation because unless the right-hand side is linear in phi n plus 1, there's no way we can extract phi n plus 1 out of this. Okay? We'll discuss how we do it in a second, but okay. So that gives us the backward Euler method. It's phi n plus 1 equal phi n plus delta t, right-hand side at n plus 1, okay? So now I want you to go ahead and try to show the stability condition for using the backward Euler method. So just like we did earlier, I want you to show that the ODE d phi by dt equal minus a phi with a positive, show that the backward Euler method is always stable. Okay, so now you know the right-hand side, okay? And I want you to show that phi n plus 1, okay, is always less than phi n regardless of the time step size. So essentially, take the right-hand side, plug it in the backward Euler formula, and show me that phi n plus 1 is always less than phi n. So take the right-hand side of this ODE, a phi, plug it into the right-hand side of the backward Euler formula, you'll get things with phi n plus 1 and phi n and time, okay? And delta t. Then all you have to show me is that phi n plus 1 is always less than phi n in magnitude, okay? Okay, you got about 50 seconds. Anyone have an answer? Does anyone have an answer so far? Brendan, do you want to share your answer?
Sure.
Yeah.
So, I mean, since you know that A is always positive, you can just find that for any positive value of phi, d phi dt is always going to be negative. And so then...
No, for the backward Euler method.
Well, right. So then when you plug in d phi dt in for r, if, you know, for no matter what h, you're always subtracting a positive value.
Okay.
Which means that phi n plus 1 will always be less than phi n.
But doesn't that apply also for the forward Euler case? Okay, so Paul has something. Paul, phi n plus 1 is okay. Okay, so that means, yeah, okay, so Paul has the answer. Okay, let me show you how you do this. So you simply substitute the right-hand side in its place. So we get phi n plus 1 is phi n minus, so plus h times right-hand side at n plus 1, and the right-hand side is minus a phi n plus 1, so that's what you get. And then simply extract phi n plus 1 in this case, so you get phi n plus 1, 1 over 1 plus delta t a phi n, and since a is always positive, this quantity 1 over 1 plus delta ta is always less than 1 because the denominator is always greater, is going to be always greater than 1, okay? So what that means is that regardless of the value of h, it's always positive, of course, because it's a time step, right? This is unconditionally stable. So regardless of what time step you choose, you're always going to get a stable answer. Whether it's accurate or not, that's not the question here. The accuracy of the backward Euler method is actually first order, like the forward Euler method, because we only use a first order backward difference, okay? So in terms of accuracy, it's no more accurate than the forward Euler method, but it is always stable. And that is what is so great about implicit methods. So graphically, the way this works, the forward Euler method approximates the slope at n, while the backward Euler method approximates the slope at n plus 1. Now, both of them, they're gonna, like in this example, they will overshoot the answer, always, okay, in this case. But the backward Euler method is at least stable. So it will give you a solution, okay, regardless of the time step size, okay? So now, I'm gonna go back to the idea of this being implicit. So in general, this equation, you cannot extract phi n plus 1. In the case we just tested for stability, we were able to get phi n plus 1 to the left-hand side in terms of phi n. But in general, that's not the case. In fact, in general, I claim that this is a nonlinear equation, okay? And I'm asking you here, explain why this would be a nonlinear equation in general. And I want you to write down the residual form. So remember, we know how to do nonlinear equations, right? So when we're solving for the root. So in this case, we are solving for the root phi n plus 1, okay? But I want you first to explain to me why this is a nonlinear equation in general, and I want you to write down the residual form. I'll give you a couple of minutes. And once you have an answer, please speak up so that we can save a little bit on time, because there's still a lot to cover. So that's the problem with implicit methods, is that you cannot extract phi n plus 1 directly. And the way you would explain this as a nonlinear equation is just, assume anything for R and then show that you'll get a nonlinear equation.
So since R could be anything, couldn't I just stick phi into like sine of phi plus 1 and therefore we'll make it nonlinear?
That's just one example that proves that this is a nonlinear. So what Emily is saying is that, okay, just take R equal sine phi. Okay, so what you get is phi n plus 1 is equal phi n plus delta t sine phi n plus 1. So what is phi n plus 1? We're solving for phi n plus 1. Well, it's a nonlinear equation, right? So now write the residual, okay? Write the residual form, because we know how to solve nonlinear equations. The first thing you do for nonlinear equations is write the residual form, okay? So go ahead, write the residual form. Don't necessarily assume sign. Keep it in terms of R, please, okay? Okay, you got about 10 seconds.
So it's non-linear because you can put anything in terms of R?
Yes, so yes. Okay, so let's go back. So Dylan is saying, just again, following up also on Emily, is that R in general could be anything. Could be sine, could be cosine, could be exponential, could be log. Just go ahead and substitute any function in terms of, instead of R, and put, for example, log t times phi. So what you get is phi n plus 1 is phi n plus delta t times log of tn plus 1 phi n plus 1. Now in this equation, what are we solving for? We know phi n, we know delta t, we know tn plus 1, but we don't know phi n plus 1. Yet phi n plus 1 is showing up in a nonlinear manner. And that makes this equation a nonlinear equation, right? So what do we do with nonlinear equations? We solve them with Newton's method, right? If you remember. And the first step in Newton's method is to write the residual form. So who can give me the residual form for this case? All right, I'm gonna go and,
So,
yeah, we got Emily. Okay, go ahead, Emily.
So you would just move the phi n plus 1 to the right-hand side. So I have, or whatever, 0 is equal to phi n plus 1 minus phi of n minus h times r of tn plus 1.
Yes, thank you. Thank you, Emily. That is absolutely correct. So the residual in this case, because R can be anything, this is just simply for the residual function, we move everything either to the right-hand side or to the left-hand side, so that the answer is when the residual is equal to 0. When the residual function is equal to 0, that's where we get the root. Okay, remember why we wrote things in residual form. So in the general case, the residual form of the backward Euler method is given by phi n plus 1 minus phi n minus delta t right-hand side at n plus 1. So where I moved everything to the left, okay? All right. So the backward Euler algorithm is a little bit more complicated than the forward Euler because it has a nonlinear equation in it, right? So the way we do this is that, the way I'm writing this algorithm over here is that you're given the state at n. So you know phi n, you know tn, you know your delta t, and you know the right-hand side, the form of the right-hand side. That's not mysterious, that's given by the ODE. First thing we want to do is, because the solution for phi n plus 1 is a nonlinear equation, okay, uses a nonlinear equation, we have to have a guess. And remember in Newton's method, when we use the guess, this is no different. So right now we're gonna guess phi n plus 1 before we get to the solution, pardon me. And then we said Tn plus 1 is Tn plus delta t, and then we solve for the residual, g phi n plus 1 equals 0. That gives us phi n plus 1. And when I say solve g phi n plus 1 equals 0, that's a Newton method, that's an iteration. So now we have the time step integration, and at every time step, we have to do a Newton solve. And if you remember when I talked about Newton's method early on, we typically want to do a few iterations. It's because of this. If you're doing a time integration with millions of time steps, and every time step you're doing 5 iterations, that's 5 million steps you're taking in total, and that's a lot, okay? So you want to use an efficient, you want to be as efficient in your Newton's method as possible, okay? And then, you know, the rest is standard like the forward Euler method. Okay, so this may still be unclear to you. Let's do a concrete example. So I'm going to take this equation, dc by dt equal minus kc squared. This is a second order reaction for some reactant, and c is the concentration, k is the reaction rate. And if you cannot tell already, this is a nonlinear ODE because the right-hand side is nonlinear, okay? So if we were to use forward Euler, we could extract Cn plus 1 very quickly, okay? No issues. But if we want to use the backward Euler method, what we need to do is first discretize this. So that gives us C at n plus 1 minus Cn over delta t equal minus k Cn plus 1 squared, okay? Now notice I moved n plus 1 and n from subscript to superscript because of what is going to follow. Okay, so this is not a power, it's an index. Okay, this is the time index. C at n plus 1 minus Cn over delta t is minus k Cn plus 1 squared. And this is a nonlinear equation. Okay, now our residual form, we defined it just earlier, is phi n plus 1 minus phi n minus right-hand side at n plus 1. So that's our residual function. Now for Newton's method, we need a derivative. So you compute the derivative, again, with respect to Cn plus 1, okay? Because your derivative is with respect to the root, right? So you compute that derivative, differentiate with respect to Cn plus 1, so you get 2k delta t Cn plus 1 plus 1. So that's, so from here onward, we did this with nonlinear methods, okay? Except now we're using it within time integrators, all right? And now you use Newton's method. And Newton's method tells you that the root at k plus 1 equal to the root at k minus the residual function at k over the residual prime at k. And that's why I moved the time index to the superscript, because I need an index for the Newton iteration, and I'm going to put that in the subscript, okay? Now, what is usually a good initial guess in this case? What would you imagine would be a good initial guess in general? So I have a lot of people on the chat. I cannot see the chat always. Please speak up if you have 0. No, there's a better initial guess than 0.
1?
No. Think about this. This is a time. Yes, Paul, thank you. So Paul is saying, we use the previous value of phi as our initial guess. So think about this. We are computing phi n plus 1 by moving from phi n to phi n plus 1. We know phi n. So phi n plus 1 better be very close to phi n. And that's true. So our initial guess for phi n plus 1 is always phi n. And then you run it through the Newton solver, you'll converge it real quick. It just takes a couple of iterations when you do that. And if you remember, I also mentioned this before, that in these Newton solvers are part of big time integrators. And we typically use just the previous value, which is what Paul is suggesting. And that's true. So when you use this, if you're implementing this, you just use the previous value of your solution, okay? So you iterate this until convergence and then move on to the next time level, okay? So now I'm gonna go back to the notebook with gaps, okay? And we're gonna do this together because also we're running, actually let's take a break. Let's take a 2-minute break, please. Okay, I'm gonna pause the recording and we will take a 2-minute break. Okay, and I'll see you in 2 minutes, okay? We are back. My young students, my young pupils. Okay, all right, so last time, 2 minutes ago, we left off talking about the complexity of the backward Euler method. So let me simplify it for you a little bit. Implicit methods allow us to circumvent the time step size stability and limitation problem. And we've just shown that the simplest implicit method, called the backward Euler method, allows you to take an arbitrary time step size without any impact on stability. So you will get a solution. Accurate or not, that's not the question. It will give you a solution. Okay, it's not gonna oscillate and just give you garbage and junk. However, implicit methods result in general in a nonlinear equation. And that nonlinear equation is this guy. Phi n plus 1 is phi n plus delta t, right-hand side at n plus 1. The reason is that the right-hand side in general is nonlinear in phi n plus 1. So why is this equation nonlinear? So we're solving for phi n plus 1, and the right-hand side can be anything in terms of phi n plus 1. If it's linear, great. We showed that Newton's method will give you the exact answer for a linear, when the equation is linear. But in general, the right-hand side is nonlinear. So therefore, we need to use Newton's method to solve for phi n plus 1 in this, for this nonlinear equation. And then we define the residual for the backward Euler method. This is a general form. Phi n plus 1 minus phi n minus delta t, right-hand side. If you know the right-hand side, you can do this for any kind of ODE. So let's go ahead and try to do this together. Okay, so we're gonna go back to the motivation for implicit methods with gaps, okay? And we're gonna try to implement this together. Okay, I'm gonna first start with the backward Euler method here in this cell. And you know, everything here is standard. We're just, we pass the right-hand side to the backward Euler method, we pass the initial condition, we pass the end time, and we pass the time step size. Okay, in there we get the number of time steps, we initialize the solution variable, etc., etc. What matters is here, is this loop over here. Here we are looping over the time steps, okay? We compute Fn from the previous, we get Fn from the existing value, previous point in the array, okay? Time at n plus 1, in this case, is the time array at n plus 1, okay? Now we need to compute F new, okay, or phi n plus 1. And according to our equation, excuse me, phi n plus 1, F new, is obtained by solving this residual function, okay? Hold on 1 second. Okay, is obtained by solving this residual function. So what can we put here? Let's say we are gonna use, and to solve this residual function, we're going to use Newton's method. So let's assume we're going to use the built-in method in Python, which was, if you remember, called fsolve. So what would we put here in this case? Here we need to solve for residual function. So if you remember fsolve, all we have to do is do fsolve, and then we need residual for residual function. Okay, give it the residual function. and we need an initial guess. Okay, we need an initial guess, and we said that our initial guess is the old value. Okay, now what is the residual function? Well, we just defined it here in the slides. So we can define the residual function over here. Okay, and in general, the residual function is going to take phi n plus 1, phi n, delta t, and tn plus 1. Okay, and the right-hand side. So it's going to take what? 1, 2, 3, 4, 5 parameters. So over here, what I would do is just simply return this residual function, fn plus 1, which is phi n plus 1, fn plus 1, minus fn, minus delta t times right-hand side. Now remember, how did we define the right-hand side of any of these ODEs? As phi t. So let me remind you of our right-hand side over here. The right-hand side was defined as phi and t. Okay, so going back to the backward Euler, what is the residual function? It's phi n plus 1 minus phi n minus delta t times the right-hand side at n plus 1. So our right-hand side, we're going to have to pass it fn plus 1, sorry, and then tn plus 1. Okay. So now I claim that this is the residual function that we need to pass to this f-solve, and I call it BE residual for backward Euler residual. So all I have to do is put the name over here. The next argument in f-solve is the initial guess, which is fn. Now, this is not enough, because if we call this, it's going to crash. So if we try to run it, it's going to give an error. Why? Because this backward Euler residual has a bunch of arguments to it. Okay? So we need to pass all of the extra arguments. In the standard nonlinear solver, if you remember when we used f-solve, the residual function only took one value, which is the current iteration, okay, where we're iterating. So we need to pass all of these extra arguments. And the way we do this is, again, through the keyword args, just like we did with ODE int. So this would be args equal the rest of these guys. Our right-hand side, RHS, which is passed through here. I know this gets really convoluted. And then fn, which is this value, and then the time step size, dt, and then tn plus 1. Okay, now when we call this, we define these functions. Over here, I'm going to call this backward Euler on the sharp transient. Okay, and I'm going to give it a time step that didn't work for us, which is 0.003. I'm going to run it and plot it, and look at that. We were able to get a stable solution. This here, this over here, is a general routine. You can use this with any right-hand side. Okay? You don't even have to understand what I did here. Okay? But you can use this, and feel free to use it in your homework, with any right-hand side. All you have to do is define your own right-hand side. Okay? But you have to understand the structure of what we did. And I know it gets convoluted because there's functions calling other functions, calling other functions. You know, that's going to be, it's not going to get easier. These programming concepts are going to get harder with chemical engineering. But you know what? You're going to get better. Okay, so better be exposed at this early on and know what you're up against, and you're going to get better. Trust me, you're going to get better as you go through future courses. But this is the least simplified version I could give for an implicit method. Okay. Now, of course, if we go for higher time steps, so let me pick a very large time step, the solution will be stable, but it's not going to be accurate. It's going to be, at least not going to be garbage, but it's not going to be accurate. It's going to give me a solution that is stable, okay? Regardless of what time step size I use, okay? Now, of course, if I refine my time step, I'm going to get a very accurate solution, okay? Okay. Now, ODE int doesn't have this problem because ODE int internally uses implicit and adaptive time stepping. It does its own thing. Okay, so what I'm gonna ask you in the homework is to actually your choice. It's up to you to use ODE int or our own integrators. My advice to you is try to use the integrators to learn something new, okay? But you don't have to. I personally, in practice, I use ODE int, okay? But at least being exposed to know how to write a function like this is tremendously helpful in my opinion, okay? Now, I'm gonna skip, because we're running really short on time, I'm gonna skip the Crank-Nicholson method. But the Crank-Nicholson method, let's skip it for now. The Crank-Nicholson method is nothing more than a different time integrator that is second order, but it's also implicit, okay? And however, rather than using the right-hand side at n+1 or the right-hand side at n, it uses an average between, it uses the average between the forward Euler and the backward Euler method, okay? And what it does, hold on. Okay, so the Crank-Nicholson method essentially takes the average between R, the right-hand side at Tn, and the right-hand side at Tn+1. It takes the average of the two slopes, the slope at n and the slope at n+1, in an attempt to get a better prediction. And in fact, it does give a better prediction in the vast majority of cases. It's a more accurate method. It's second order, okay? So if you cut the error by half, if you cut the delta t by half, you're going to get the error by a factor of 4, okay? Again, this is a nonlinear equation. The residual equation is this guy. You know, these methods, they become just routine once you know the backward Euler method. What I want to get to before I finish off with this lecture is actually systems of equations, because that's on your homework. And that's something I had a very fun problem that I wanted to do together with you. But the vast majority of cases in initial value problems are systems of ordinary differential equations, okay? And solving a system of equations is no different than solving a single equation. You just rather than solving one equation only, you solve 2 or 3 or more equations. And typically those equations are coupled with each other, okay? What we're gonna do here is use ODE int for systems of equations. We're not gonna implement our own routine, okay? The way we write a system of equations is write it in vector form, is write dy by dt, where y is a vector of equations. I should have put the example beforehand. Let's put this example. I was so excited about sharing this example with you because it can be used to model the COVID epidemic outbreak right now, okay? So these three equations, they're called the SIR model for the spread of disease. Okay, it was developed in 1927, very long time ago, but it's still a very powerful model. And honestly, it is no different than what the CDC and NIH are currently using to predict our outbreak. Now, of course, they have different data to fit the parameters, but the idea is this simple, honestly, is this simple. So these are 3 ODEs. Physically, what they're describing 3 types of people. Those who are susceptible to get the disease, they're called S. Those who are infected and infectious, called I. And those who are recovered. And typically what happens, people from the susceptible category, they get in contact with people who are infected, and then they themselves become infected, okay? Now, those who are infected, they recover at a certain rate, okay? Currently, it's about 14 days for recovery, right? And then they move to the recovered category. However, those who are infected, they still infect people from the susceptible. So if you look at, you know, what I'm showing here in the plot is a solution for one set of parameters you see in the equations beta and gamma. Beta tells you the average infection rate of the disease, and gamma gives you the average recovery rate of those who are infected. So you see in the first equation, there's a negative sign on the right-hand side, which means people in the susceptible category are being reduced because they're being consumed by the infection. They move into the infected category at the rate beta. But if you look at the second equation, which is the infected equation, people are moving out of the infected category at the rate gamma. So there's a minus gamma I, and they're moving in at the rate beta. Okay, and then at the end, the rate of people being recovered is going to the recovery is I. Now you look at the curves. The blue is susceptible, the red is infected, the green is recovered. Starting with a fully susceptible community, 100%, there's like one infected person in red. And then the number of as the number infected grows, the number of susceptible decreases, okay? But also the number of recovered increases because people move from the red category to the green category. And this is, you know, this is when we talk about flattening the curve, it's the red curve that we want to flatten. Because in this model, what I'm showing here is about 60% of the population is going to get infected at the peak. And that is going to be beyond any hospitalization capacity. So the question is, how do we manipulate beta and gamma, okay, to flatten this curve, all right? And that's a legitimate system of ODEs that we need to solve. So how can we solve this system of ODEs? We can use the forward Euler method, we can use the backward Euler method, but all of these equations are coupled with each other. So you're going to have variables from the first equation requiring variables from the second equation and so on and so forth, right? Because they're all coupled with each other. And that's why they are a system of equations. What we're going to do, we're going to use ODE int to do this. Now, there are 3 equations here and 3 right-hand sides. So the way we write this is by writing this in vector form. So we write a vector of left-hand sides and a vector of right-hand sides. Okay, and now each right-hand side can depend on all of the other variables. Okay, so the first equation could depend on the variables from the second, third, and any kind of equation subsequently in the system. ODE int is great because it not only solves one equation, it can solve a system of equations. For one equation, we provided ODE int with one right-hand side, one initial condition. Okay, the time domain is still a time domain. It doesn't change. It's an array of times, okay? So we're running out of time, but if you can give me 7 minutes, please, it will be worth your time, okay? It will be worth your time. Please, thank you. So ODE int can take a single right-hand side for one equation and a single initial condition. For vectors, do you think it will work for systems of equations? Absolutely. Instead of passing a single right-hand side, we pass it a vector of right-hand sides. And we pass it a vector of initial conditions, okay? Now, we said that the right-hand side was defined in a way that depends on phi and t, or y and t. Now, each right-hand side is going to depend on the entire vector, okay, of equations, all right? So let me show you how we do this. Download from Canvas the system of equations for the SIR epidemic model with gaps, okay? And we're going to do this together. And you're going to go home, you're going to play around with the parameters to come up with a way to flatten the curve, okay? So go ahead and download the system of equations, SIR epidemic model with gaps, okay? Suddenly outside, it's like the apocalypse. There's like so much wind. I swear I saw a tree fall. It's just got so windy outside.
Maybe it's because you're in space. I don't know.
Maybe, but there's no wind in space. Maybe I'm
It is
seeing
true. I forget about that.
That is true. Unforgivable mistake, but that's okay. All right. Okay. So do we all have the epidemic with gaps? It sounds morbid, but it's very empowering to see something that a model that you can play with and make predictions. Okay, so initially we have a bunch of imports over here. Just run those, okay? And this is the model for epidemics, all right? It's ds by dt is minus beta is, and di by dt is beta is minus gamma I, and dr by dt is gamma I. Now, the way we're going to program this is we're going to program a vector of right-hand sides. And we're going to decide that we're going to solve these equations in this order, S, I, and T, S, I, and R, okay? So our right-hand side is going to depend on a vector of dependent variables. So if you look at this condition over here, RHS YT, that Y is a vector, okay? It's a vector of the dependent variables. So this vector, when I define the RHS for the SIR model, I'm gonna call this vector SIR. So SIR is a vector of solutions, okay? So that's what I'm saying here. So my right-hand side, okay, is gonna depend on at least the dependent variables, in this case, and time. But I also wanna pass, hold on, let me get rid of this guy actually. Yeah, let's keep this guy. Okay, and I also wanna pass, I want to pass a few more parameters, okay? I wanna pass the population size. Okay, so there's another way to write this. Let me fix it, give me a second. So this is beta over n. I apologize. There are multiple ways of writing this system of equations. Beta over n, and yeah, so that's the right-hand side. Okay, sorry, apologies. There was a typo in the equations. There are different forms of the equation. All I did here was divide beta, a parameter a knob that we can tune. I divided by the population size, okay? The population size is something that we choose. Say we're gonna try this for Salt Lake County right now, which is 1.2 million, the population, okay? Okay, all I did was divide by n, all right? So now the right-hand side for this model is gonna return these three right-hand sides, okay? So now given these three S, I, and R as a vector, given time, I need three more parameters for the right-hand side. I need n, the population size, beta, and gamma, because we don't want to keep hacking the right-hand side. We want to be able to pass those as arguments, like we did with ODE int with the lobster example, okay? Now, the way you extract the different variables is you take this vector and just do this, S, comma, I, comma, R. That is going to return the three solutions from the vector of these solutions. The reason is that I'm defining my solution vector as a tuple. As you know, in Python, you can return variables separated by a comma. You can define them as an NumPy array. It will become an array of arrays. Gets really complicated. I like to define them this way. So this is much easier. Now, the right-hand side for S is simply minus beta over n times I times S, okay? The right-hand side for I is beta over n times I times S minus gamma times I, and dr by dt, the right-hand side for R is simply gamma times I. That's it. And now what do I return? I need to return a vector of right-hand sides in this order. So I need to return ds by dt, or right-hand side for S, di by dt, or right-hand side of I, and dr by dt, or right-hand side of R. And that's all that takes to define a system of equations. The rest is simply setting up the problem. So let's see what I've done here. I started with the following numbers: a population of 3,000 people, okay? An initial number of sick people, 10 sick people initially. See how they're gonna infect the entire population, just 10 people, okay? Initially, I'm gonna have 0 recovered people. So these 10 people, you know, they traveled here and they started infecting everyone else. And now the initial condition for S, the people who are susceptible, because the total population is n, we defined R 0, and we defined the initial number of infected. Then the initial condition for S is n minus all of those guys, because that's a conservative system, right? The total population needs to be n. Susceptible plus infected plus recovered needs to always be equal to n. That's the total population. No one is coming in, no one is leaving. So that's how I define my initial condition for S0. Okay, it's minus I0 minus R0 actually. Okay. All right, so I'm gonna start with the following: beta equal, let's say 0.4, and gamma is equal 1 over 14. Now, if you read the literature on this, gamma is 1 over the number of days a person is infected. And for the SARS-2 virus, it takes 14 days on average for people to recover. So we're going to take gamma as 1 over 14. And then we'll see how to play with beta. Next, I'm going to run this for 100 days. Okay. Now over here, time is in days. Okay. I'm going to run this for 100 days. And then simply the lin space is from 0 to t end. Okay, remember, so in this case, time is really meaningless. You assign to it whatever unit you want. It could mean 100 seconds if you want. But over here, the meaningful time is actually in days. And our time step is going to be 1 day. So the way I'm doing this, I'm creating a linear space from 0 to 100 days with 100 points, with t end points in it, okay? Okay, all right. And then we define the initial conditions vector, and then we get to ODE int. For ODE int, we need the right-hand side. So it's right-hand side, sir. Y0 is these initial conditions, and the arguments n, beta, and gamma, and we can just solve this. And now what I want to get to is this point over here. So what I'm plotting here is the population of susceptibles, infected in red, and recovered. Okay. Now what matters here, to flatten the curve, you have to manipulate the infection rate, this beta. And social distancing has the effect of reducing that infection rate. So if we go from 0.4 to 0.2, okay, let's see what happens. The curve has flattened. Okay, the curve has flattened. The epidemic is lasting longer now, but because we're social distancing, we're affecting beta, and the peak infection here is about 30%. Okay, it's about 30% over here. Okay, so let's say what happens if people recover sooner. So let's say they recover in 5 days. What do you expect will happen? It's going to get even flatter because they don't have time to infect others, right? So you run this, it's just, you can't even see it. You have to run it for maybe 500 days to be able to see where the peak happens. You can't even see the peak when you run it for 500 days. So let's go, on the other hand, to like 30 days. Let's say that's like the nastiest pathogen ever. You get sick for 30 days and you infect everyone in your path. What's going to happen? You're going to have a really strong peak early on and a very high peak because you're very infectious. You have a longer period of time to infect people. Okay, so how do we fight this? We don't have much control over gamma, which is the length a person is infected. We have control over how limiting the interaction between the infected and the susceptibles until a vaccine is discovered. Okay, I'll let you go. Thank you for spending this extra time. I know this went by a little bit quick. Try to redo these exercises again. Go back over the lecture. Try to redo these exercises. I'm going to ask you to use ODE int. So all you have to master is using ODE int in your homework. Okay. Thank you for your attention. I really appreciate your staying in. We're almost done. We have just 3 lectures left. Okay.
Oh.
I know. It's anyway. It's been a roller coaster, but thank you so much. I know if you have questions, we'll let everyone stay for your questions if you want. But I know you, yes.
Is there a quiz today?
No quiz, but there's a survey on Muddy and Clear Points. Go ahead and take that so that I can address concerns in a document. Thanks, Gary.
So there's more like different methods for solving for ODEs, like the Hune method or the Runge-Kutta. How do they differ like from the Euler method?
They're all part of the same category. So the Runge-Kutta method is essentially, so there's explicit and implicit Runge-Kutta methods. And what matters is what goes in the right-hand side. Do you interpret things as n+1 or n? All of these Hoynes method or the midpoint method and Runge-Kutta, they give you more accuracy. They give you higher order, okay? And so they get order delta t squared, delta t cubed, delta t to the 4th. And Runge-Kutta methods is essentially the way it works. Within a single time step, you take smaller time steps within a single time step to get a better approximation to the derivative, okay? But it turns out it's a little bit more efficient than taking more time steps with the forward Euler method. Okay, so you know, if you know the forward Euler, you can read up about the Runge-Kutta. I did put in some reading material for ODEs in the files directory. They talk about Runge-Kutta method, but Runge-Kutta methods are simply an extension of the forward Euler method. But you're not responsible. We're not going to cover those in the class. There's not time this year. Okay, but they're not. If you know the forward Euler method, you know how to use Runge-Kutta. You'll learn how to use Runge-Kutta methods. Okay.
Thank you.
Thank you. Any other questions? Okay, I will see you next Tuesday. Okay, thank you very much.